Don't really have to have memorized, but I'm going to write it out for you because I want to refer to these as A, H, and K. So vertex form of a quadratic, y equals a x minus h squared plus k. And I'll come back to these additional thoughts when we start, actually graphing these. But I said, what would the key points be when the a value gets stretched by 2 or by 3 or by a half? So we'll come back to add that onto this resource page when the time comes. A is just like the transformation rule, and it tells you if you get stretched or shrunk, and it tells you if you are concave up or concave down. So we're going to kind of put those rules on there. Concave up when A is positive, concave down when A is negative. We're going to keep referring back to A, this unit on graphing. What is the H value responsible for? So when we had like x plus 3, what did it do? Shifted it which directions? Left or right? So when H is positive, we move to the left, and when H is negative, we move to the right. Right? X minus 3 moves us to the right. X plus 5 moves us to the left. What's the K value in charge of? So up when K is positive and down when K is negative. So it's the same transformation rules that you have already seen, just written out for a quadratic. And we looked at the parent function of the quadratic yesterday. So the parent function is on kind of the previous page, but the parabola is 0, 0, 1, 1, 2, 4, and 3, 9 is the graph of that parent function. We're going to use that to graph these other functions. So it's back a page if you want to flip back to it. So what two things have happened? What's the plus 1 do? And what's the minus 4 do? Theodore? Yep. And? Perfect. So left and down. So I'm going to find my vertex by going left 1 and down 4. Don't put a dot at negative 1. Go to negative 1, comma, negative 4. Sorry, kind of faded on this printout. There's my negative 1, negative 4, and now I draw the parent function. So the parent function goes over 1 and up 1 for a parabola, because 1 squared is 1, and then 2 squared is 4. So from the vertex, if I go over 2 and up 4, I end up right on that x-axis, right, because that would be up 4. And then 3 squared is 9, so if I go over 3 from the vertex and I go up 9, I would be at positive 5, because I'm starting at negative 4. So if I add 9, I'd be at positive 5 up there. So here I am. There's my parabola that's been shifted, what did I say, left 1 and down 4. So on Monday, we're just going to be practicing with a quadratic over and over again, graphing a transformed function on the graph. So let's do example 2. I think the next page is standard form, right? So we're not going to do standard form today. All right, so here's example 2. What two transformations have happened to this function? Yep. Left 3, and it's being flipped over the x-axis. So concave down, flipped upside down. So I'm going to find my vertex by going left 3. There I am. And then I'm going to just flip that parent function upside down. So I go over 1 and down 1, over 2, and I would be down 4. So I'd be at negative 4 from the vertex. And then over 3, 3 squared is 9. So I'm going to be right at a y-intercept of 9. And I just draw across from it. It's symmetrical, right? So all these points are symmetrical across kind of that line of symmetry that cuts this graph down the middle. That's a line of symmetry. So all we graphed were the parent functions. But guess what? This graph could get steeper or less steep as well. And so that's what I want to put here about the key values when you stretch or shrink your A value. Are you guys good with that graph before I move it? Speak now. All right, so while we're on this resource page, I just want to list the set of points again. So usually our set of points are the vertex will be at 0, 0, then you go 1, 1, then you go 2, 4, and then you go 3, 9. Does it make sense what I'm talking about? Like from the vertex, those are your moves, right? To get those points. Because 1 squared is 1, 2 squared is 4, 3 squared is 9. What happens when I stretch my function times 2? The height of the graph is going to double. So 0, 0 stays at 0, 0. It doesn't shift where the vertex is. But 1, 1 becomes 1, 2. My graph is twice as tall. And 2, 4 becomes 2, 8, because 8 is twice as tall as 4. And then I usually don't graph the 3, but it would be 3, 18. So I'm doubling this value right here, but I'm keeping the x value the same. So I want you to do the same thing. What if I stretch it times 3? So I'm only going to do the 0, 0, the 1, 1, and the 2, 4. So what if I stretch those points 3 times as tall? Well, the vertex doesn't get moved. It stays in the same point, and I'm stretching these y values over here. So what would I do for my next transformation? 1 would go what? 3 times as tall. And what about 2? 2 would go 3 times as tall and be at 12. So that's a lot steeper, right? I'm going like this, like really tall, instead of like this, maybe the parent function. So you're stretching the height of the graph. The last one I wanted to write down on here is what happens if I shrink the graph this time? So this time I'm actually going to do one extra point. 1, 1, 2, 4, 3, 9. What would be that last point? If I went 4, what would I have to go? 4 squared is usually what? 16. So let's think about cutting the height of this graph in half instead. So I'm trying to emphasize your x value stays the same. You only adjust your height of the graph. So you'd have 0, 0. What about for 1? Well, if your half is tall, half of 1 is a half, right? So I'd be at 1, 1 half. All right, what about 2, 4? What's half of 4? So I'd be at 2, 2. What's half of 9? Yeah, so it's okay to have a decimal. If you're cutting something in half, it might not be an integer. And the reason I wanted to go to 416 is because 4, 8, that will usually fit on the axis that I give you. And usually I say like plot all the points that fit. So think about what this is doing. This is taking your parent function and now you're only half as tall, but you're starting from the same point every time. So you've got these sets of points. When we start doing them on Monday, you can refer back to them. Let's just do one last one from, that's all right. We're done.